They say that change is the only constant in this universe. I bet Mr. Faraday would agree with me because it is this change that makes electricity possible. Most importantly, the ability of certain elements to resist this change is what makes achieving spectacular results possible. Yes, I am talking about the magic of inductors. Today, let us try and intuitively understand how an inductor can help us boost DC voltages in a boost converter. So, let's get started. What we have here are inductors, which is basically a coil of wire wound on a ferromagnetic core, or none at all. Now, if I wire it up on a breadboard according to this circuit and power it with the DC voltage, let's see what happens. When the switch is closed, the current passes through the inductor and energy is stored in the magnetic field. When you release the button, the current through the inductor tries to stop suddenly, so there is a change in the current. Whenever things change, as humans, we have two options: either to accept it and move along, or to fight it and resist the change. Oftentimes, the latter is the most difficult, but also the one that leads to magical results. The same is true here. Our little inductor tries to resist the change in current, but to do so, the only way is to act like a power source by creating an opposite voltage across it, thus maintaining the current flow in the same direction. To do this, it uses the stored energy in the magnetic field and fights the change. But eventually, the stored energy runs out and it goes down fighting, just like how a compressed spring would rebound till the oscillations fade. The oscillations you see here are as a result of resonance with the parasitic capacitance across the inductor. To know more, you may please refer to this video link on your screen, where I talk about resonance in detail. Moving on, what we can learn from this, besides the obvious life lesson, is that the inductor creates a voltage that is many times higher than its supply voltage. Though it lasts only for a fraction of a second, we can put it to good use in boosting DC voltages if we think cleverly. Let us consider the following analogy to get an intuitive understanding of the whole process. Consider the whole setup as water stored in a tank. The water represents the charge. Let the voltage be analogous to the pressure of the water at the outlet, which in turn is determined by the height of the water in the tank. The higher the water level, the more the pressure. The current is of course the rate of flow or discharge of water through the outlet pipe, and the area of cross section of the pipe represents the resistance. The bigger the pipe, the lesser the resistance and greater the discharge. Also, water flows always from a region of high pressure to that of low pressure, just like electric current, which flows from higher potential to a lower one. I hope that gives us a foundation to base a comparison on. From here on, let's try to think in terms of these comparisons to better understand the working. If you look carefully, each time the button is pressed and released, our inductor acts like a pump, pushing the water from the source to a greater height. In other words, boosting the pressure. This can be seen from the voltage spikes observed in the oscilloscope. However, this pressure boost is not of much use to us until there is some mechanism to store the water that is pumped out. Otherwise, the water just squirts from the pump and is wasted. We can try and fix that by connecting the output of the pump to a storage tank. In electrical terms, what better element can be used to store the voltage? A capacitor, of course. In an analogy, we can accurately represent that by a storage tank and with the water level in it representing the charge. If our theory is correct, each time the pumping occurs, the water in the tank must rise above that of the input because of the pressure boost from the pump. So now, let's connect everything up and see what we get. The oscilloscope is now wired to read the voltage across the capacitor. Initially, when the circuit is powered on, the voltage across the capacitor is the same as that of the input voltage. So we can see that the water level is the same in both the tanks. Now when I press and release the button, the inductor outputs a voltage spike, and you can see that the capacitor voltage rises above the input voltage for just a moment and falls to the supply voltage again. Clearly, there is something missing here. The water level in the storage tank rises but flows back into the source when the pumping stops. So, what we need is a one-way valve which only lets water flow forwards but not backwards. In electronics, we have just the right thing for the job. It's called a diode. Now that we have our circuit rewired according to the schematic, let us test the results. When I press and release the button, the pump/inductor boosts the pressure/voltage, and the one-way valve aka diode is forward biased, thus charging up the capacitor or in other words, filling the storage tank with water. I hope you can follow this line of thought. When the pumping stops, the diode is reverse biased and the valve closes, preventing the backflow of water. Now, if you repeat the process again and again, the water level in the tank keeps rising. You can see that clearly from the oscilloscope where the capacitor voltage increases with each switching and maintains the boosted voltage. So, we have successfully boosted the input DC voltage, right? Well, not quite. We are forgetting the one thing that we built the circuit for. It is the load. We can say that the load is analogous to someone opening a tap connected to the tank and drawing all the water from it. So, let's rewire the circuit to include the load as shown. Now, if we repeat the experiment, we see that the voltage once again keeps falling back to the supply voltage level. I wonder why. Of course, a pump is not running fast enough to fill the tank quickly. So, when the load draws all the water from it, the tank becomes empty. What can we do to fix it? Maybe try running the pump at higher speeds perhaps? So, let's quit the manual switching and use a MOSFET instead. They have very fast switching speeds and are much efficient in comparison. To switch the MOSFET, let us use a square wave whose switching frequency we can vary as per our needs. Ideally, a function generator would do that, but I don't have one. So, let me use variable frequency or duty cycle square wave generator. Again, let's wire up the circuit according to the modified schematic and test it. If I switch on power and start increasing my switching frequency, you can see that the MOSFET is switching faster and faster. In other words, the speed of the pump is increasing with the increase in switching frequency. If you look at the capacitor voltage, you can see that the gap between the voltage spikes get reduced with the increasing frequency. This means that a pump is able to fill up the tank much quicker. At the correct frequency, the rate at which the water is drawn from the tank matches the rate at which we fill it up, so that the water level in the tank is stable and can easily supply our load draw. This, ladies and gentlemen, is a working boost converter. Let me just point out one more practical scenario and wind up the experiment. In real world, you can never predict that your load will be constant and it is always subject to variation. For example, you may need more water during the evening and morning times than you would need in the afternoon from your apartment water supply. So, our system must be designed such that it can hold the water level at any height that we desire, at the same time ready to supply any kind of load. What we need for this is some mechanism to sense the water level in the tank and adjust the pump speed accordingly. Likewise, in a boost converter, we can use a simple voltage divider to measure the output voltage and feed it back to a control logic to automatically increase or decrease the switching speed to hold the output voltage steady irrespective of the load changes. This way, we can achieve true control over the output voltage. Actually, I could attempt to do that using an Arduino, but that would surely be an overkill. Besides, it is a lot of effort and would be inefficient. Luckily, boost converters are available in these ready-made and cheap modules that can offer DC voltage outputs of up to 40 volts and with decent current capacity. One look at its datasheet and you see all the concepts we discussed just now put to good use. You also have the circuit diagram and the component selection guide like how to choose suitable inductors, capacitors and switching frequency just in case you wish to create your own boost converters. So, this was an attempt to understand in principle how a boost converter works. I hope I was able to succeed in that. If you think so, please don't forget to hit that like button. If you think I've earned it, please consider subscribing to my channel and press that bell icon so that you always get notifications to the new contents I upload. Share the video with your friends and of course, let me know what you think about it in the comment section. Thanks for watching. Until I see you next time, don't forget, engineer, experiment, educate.